It's Hyderabad to co-chair this session. And Dr. Prema Juyu and Dr. Harshia Banu will note the proceedings of this session. In this session, we have 4 presentations, and we'll begin with the presentation from Dr. Satish Parekh sir, and then we have presentation from Dr. B.M. Prasanna sir, and then from Dr. Jarka Rashid, and then we have a presentation from Dr. Sobi SB. Now I'll hand over the session to Dr. P.U. Krishna sir.
Just looking for my rapporteurs. Please.
Hello everyone. So, had your good lunch? Now, I do not want anybody to sleep here. And for that, big hello. So, with all due respect to Krishna sir, Arora ji, and talking about my presentation, it would be good, like, if I had a screen over here, but then I used my phone, I'm using the technology to go through it. So, now we have maize session. So let's talk about maize. We can go to next. So because they have put it at the first screen only, so I will say, like, I can introduce myself. I am Satish Parekh. I am very young for Dr. Tiku to be in the industry, because when he already joined the service, at that time I was just maybe still to be born. So, but then I am 30 years in the industry, and out of that 15 at one place only, that is Koteva. And other than that, worked at ICRISAT and ICR as well, so I know both sides of the table, probably a little bit under my Gurujans. So talking about corn, let us go to next slide, please. Okay. So if you look at corn, why talk about corn? It's an important crop. And now, scenario is changing very much in India. If you look at by 2030, so 60 to 70 million metric tons, and by 2047 we are imagining that it could be 110 million metric tons. That is what is going to be the demand for corn. Now why? There are so many things which are leading to that demand, and there is a very much shift from corn as a normal crop to an industrial crop. That is what is happening in this country. Because of what? It is that is suitability of biofuel. Environmental footprint is less than crops like sugarcane, like rice. It doesn't demand that much of water. Prabhu sir, don't mind it, please. So, demand for feed and processing. Strong policy backing is there for ethanol. Like, you all know that government wants to blend around 30% now. So, sustainable alternative to water use intensive crops. Strategic advantages are also there with maize crop. Why? Because high productivity among the cereals with lower water requirement. Year-round cultivation is possible. Climate resilience and everything you also know. Greenhouse gas emissions you also know. Now there are certain challenges also in this country. And why I am putting those challenges forward? Because we are sitting in a place where our government sector partners are also there. And they do a lot of basic innovations, and we expect them to do a lot of basic innovations which take the crop forward to the next level, and that is what is required. So key challenges are dependence on monsoon, lot of rain-fed area is there, hybrid adoption and inconsistent seed availability. Seed availability is still a challenge. Government is doing a lot of work for promotion of HYVs. Gaps in drying, storage and market assurance. You all know that that causes aflatoxin issues. Quality issues in DDGS, because that's an animal feed, that quality is also important. There are lots of areas of expansion. you may call it as seed replacement rate, and how many farmers have access to seed. You know, there is an institution that also does the access for seed index. So those things are also important. Area expansion to certain states is also important. Some of these states have very low seed replacement rate in terms of HYVs. Then high ethanol recovery and diversification could be another area where opportunities exist. And resilience on the, and then reduction of the crude oil imports. That is also one of the primary things. Based on that, if you think of, there are so many research and technological priorities to come up to the standards of EBP 30. Germplasm diversification could be a very big thing through genomic selection or other methods. Then regional seed hubs, strengthen CGMS-based systems, like, you know, some of the crops like palm millet and rice have a very good CGMS system. For that sake, palm millet is a very, very extremely good crop. Then integrated solutions for aflatoxin, stalk rot, and other diseases. Now, if you look at the ecosystem, I highlighted something, and that is there are over 15 improved hybrids, more than 65 plus MOUs, still counting, every day MOUs are happening. And then 35 plus seed companies are there. Breeder seed indents are also, like, you know, increasing day by day. Collaborative efforts, expanding seed production hubs across Indian states. There are so many industrial and economic prospects. They are more like, you know, additional uses or secondary or tertiary uses from the corn. So let us not expand more on that. Now, there is a certain key message which I wanted to deliver on that. It's not all about the NBTs, because, you know, there are so many molecular biologists in the room that will tell you that a plethora of technologies do exist. But I just covered a landscape saying that, you know, when we talk about gene editing, gene transfer technologies, XYZ, you know, that gets misspelled by some of the community, saying that, you know, anything related to gene, it could be transgenic. So basically speaking, in true breeding sense, if you call them, they are not transgenics. These are more like new breeding technologies. So what if we start promoting the word new breeding technologies? That could be more important, because that really concisely depicts the thought process behind what we are doing as scientists today. So if you look at, there are precise targeted DNA changing technologies are there, like CRISPR is there, which is very, very affordable also, cheap also, very easy also, and does a lot of good job. And then for specifics, there are like TALENs or ZF nucleases. Then there are another mutagenesis methods using the ODMs. And then there are reverse breeding technologies, like, you know, you can, rather than, you know, earlier days, some of the people say that they used to break hybrids. Now that is not required, because you have reverse breeding technologies. You can use RNAs just to stop the chromosome getting recombination will be stopped. Meiotic recombination will not happen. And then you can have parental chromosomes directly inherited, and you can go for complementarity. And you can utilize through those complementation, you can actually develop the hybrids much more quickly. So those kind of things are there. Grafting of GM root stocks is there. Cisgenesis and intragenesis, where these things are delivered, although you can do that cisgenesis traditionally also, like, you know, we have been transferring those genes of importance into the same species, but that can also be done now through new methods. And then always there is a speed breeding coupled with all these technologies to bring in quicker generation turnaround time. So these precisely put together can be called as new breeding technologies. Now coming to regulatory scenarios, how we see. So this is a map which was edited by the site in 2024 probably. Out of that, if you look at, those are no restriction zones which are dark green. And then those are where approvals are required in lesser green. And then the other ones are there, red ones are there, where those are not allowed. So, but after this, there has been a change in European Union, because SDN1 is now approved for a European Union. But still herbicide tolerance is kept out of that, because still that is treated more like SDN3, and approvals are required. So I have provided an additional link also on the presentation. That is the place where you can go and find this map. I don't know how fast they will once again update it. But Now, when you look at regulatory scenarios in India, so SDN1 and SDN2 events are more often they only require the IBSC to present them and document them. Otherwise, mostly they are exempt from the DNA regulations. But wherever you talk about SDN3s, which actually involves the gene sequences, insertions, and other things, so there only GMO regulations are applicable in India. So this is very, very fortunate. Like, you know, for rice, they have mutated the GN1A gene, and you see the change has happened. It is more like changing the harvest index of the crop, because you increase the number of grains that a panicle can produce. And then, you know, this could have been done by normal breeding technologies that we are very much used to in lot, that would have taken a lot of time. So these technologies present a lot of opportunities for us. If you see progress across crops, this is not directly related to corn, but just wanted to give a small snapshot to you. Like, you know, now you're talking about GABA tomatoes that have chemical that can lower your stress and reduce your BP. So stress reliever, some kind of a thing, that is becoming more popular. Mustard greens, then fungal resistant wheat or non-browning lettuce. These are some of the examples where crops have been released across the globe, and these are the live examples of how people are utilizing NBTs to develop the new crops. Now, when we talk about crops, especially maize, this is a very busy slide, but I can tell you, if you look at purely that segment of, if you look at the maize, then, you know, haploid induction or those diseases that we talk about, all the 6 important diseases, NCLB and others, then low phytic acid and high amylose, and then kernel number per plant. So these are some of the important traits in maize. So they are like, you know, more amenable for targeting. How much we have targeted in our institutions, that is still a question to think of. So now, this is a very busy slide, but I am just trying to think of an idea, like, you know, I just want to throw an idea to the hall, that are we going to be, when we have commercial institutes, like, you know, private companies do not afford more than 1 or 2 breeders, or maybe if those programs are very big, then maybe 3 or 4 breeders. But, you know, look at the institutes and look at the universities, how much big talent they have. And if you pool the talent across the universities and public institutions, including that of CGIR, then a big, huge talent pool is available. And then, you know, there are a plethora of genes. This slide would have been very small one if I would have thought of accumulating everything across the globe, whatever is going on. Why not in India? And any of these, not only for the crops like corn, but if you speak of rice, you know, there are very less number of examples to be counted, like GN1A, that's a very good, like Dr. Satyendra, what he has done. So, or you know, what Corteva has done, like, you know, pulling up all 4 genes together for resistance. So, utilizing the HT1 genes. So the thing is that in our institutions, what are we going to do? Do we need a change of mindset? Like, you know, are we going to do basic research that will change the crop's future going forward? Now, in the university, when we were going across, going through the fields with Dr. Pathak, we found that, you know, for some of the things like, you know, naturally growing the crops, there is data available for almost more than 20 years. That is just amazing. But what about, like, you know, this is a global study where US government created that study. I have not included the Pioneer Corteva example. Corteva has done an example of analyzing they call it as era genetic gains. So those studies were conducted, but this is from the USDA data, which shows the data analyzed from 1930s to 2010. And you see that what is the conclusion, that through normal breeding, which we usually called as a conventional breeding, also there is a no plateau for the genetic gain. But yes, of course, it happens thorough slowly. Now, increase was approximately 128 kgs per hectare per year from 1934 to 2020. Now, there was a study on the short season hybrids which said that it was 105 kg per hectare per year, so almost 1% annually. But they also did not observe any plateau. But now if you see the lower side, which is highlighted one, that what they found was, if you talk about resistance genes, then those are the genes which you incorporate. Of course, these examples are not from gene editing, but these are purely like, examples of transgenics. But if you look at biotic resistance, that is the one very low-hanging fruit. If you change the biotic resistance from a susceptible to a resistant component, immediately your yield levels increase, your yield sustainability increases, farmers' profit increases, so these are considered as low-hanging fruits. How they fit into the genetic gain delivery? So everybody knows, many of you are breeders, and you all know there is a breeder's equation. So if you look at the breeder's equation, so selection intensity, when you talk about genomic selections, shelf and test strategies through genomic selection, which help you utilize large number of data sets you can create, and you can hypothetically test large number of hybrids, just a test and shelf. So utilizing genomic selection, large evaluation sets can be created and visualized. And some of those studies have reported that 0.6 is the selection efficiency for genomic selections. It can be gained, 0.6, 0.7 also, if you use additional covariates. Now in those situations, practically speaking, this becomes equal to our field trials. Because if you look at field trials also, that same kind of efficiency it delivers. Then, so selection intensity can be increased, selection accuracy, correlation between the predicted and true breeding values, I just now talked about. Then additive genetic standard deviations, utilizing the additive genetic variants. So when you talk about editing epigenetics for novel germplasm creation. So epigenetics is basically not to transfer, some of that is transferable also, but majority of it is just for studying whatever you have created, or suppose if you want to study a gene, so you cause it could be DNA methylation or something else, so you cause epigenetic variations and try to study the gene pathways. So, but that is not heritable. Some of the cases it is, of course, but these provide you, and editing directly, grain number gene. So those provide you chances of creating an additive genetic variation that can be directly utilized into your breeding system and breeding pathways. Then cycle length. When you talk about double haploids, those F8 generation comes to just one generation. And then speed breeding. So wherever that is not possible, double haploids, of course, corn is a lucky crop to have double haploids, but some of those recalcitrant crops, like pearl millet, still people are trying, but some of those crops are very recalcitrant and they do not respond to DH. So then, in those cases, speed breeding is an additional alternative. So these are all the new breeding technologies. If you look at them, most of conventional breeders, probably like me, would say that, arey yaar, ye biotechnologist kya karte hain? But technically speaking, all the streams of this science, maybe it is pathology or maybe it is biotechnology, everything can be harnessed to deliver the genetic gain. Big examples, Genelytics from Corteva. So they have done multiple editing, 70 plus edits in one plant. I think many colleagues should be from Corteva here. So, and then AI-guided target discovery. So 3 to 4 higher genetic combination rate they have reported. Multi-gene disease resistance. So that also has been reported. So multiplex editing has been reported by Corteva, and they have published it. CIMIT and other Grover partners, that is also a very famous example. So for lethal necrotic virus, they have delivered that they have solved the problem of African continent, and they have delivered this really to on the ground. So now, what are the bottlenecks that were solved through these NBTs? So transformation, that was a limiting factor. They resolved it. Now it has become transformation independent. Directly it can be delivered. Polygenetic quality traits, they are very, very slow to improve, but that is also possible through NBTs. And then hidden deleterious alleles that reduce the genetic gain. So for that also, knockout is an answer. So that is one AI generated corn. So why it is important for corn now? Precision genome editing, multiplex gene editing, overcoming transformation bottlenecks, biotic stress resilience, and global food security. These are the key challenges in front of us, for which, especially in today's context, and more so in Indian context, because we are targeting reducing our, foreign exchange deficit by importing less and less crude oil. So then, it becomes too much important for us. And somebody quoted, I know many of us are non-corn people. I am also one of the non-corn breeder. But we feel or don't feel, one of my colleague who breeds corn, he told me one day, oh, you grow corn and leave everything. You can sell corn and buy anything else. So NBTs for biotic stress tolerance in corn. When we talk specifically about, now see, fall armyworm, and those in the bottom, they are the percentage of losses that happens by these biotic stresses. Fall armyworm causes losses to the tune of 35% on an average. Stem borer, again same example, another 25% of losses. So like that, TLB, so if you talk about it, is almost 15% of losses. So as I was sharing with you that entomological, pathological, weed competition, nematodes, these are all the kind of biotic stresses that cause problem to the yield delivery or yield sustainability or adoption of yield in one state and not in the other state. Say, for example, the corn hybrids that can grow in North Karnataka may not be growing in South Karnataka. So those are the differences. Those barriers can be crossed if we utilize NBTs and try to make changes. What is the value proposition for us? Protecting the genetic gain, it increases the resilience. Biotic stress is a throughput but bottleneck also. As far as I know from the private industry, if you are developing 100 hybrids, every year 30 to 40%, almost 30 to 40% of hybrids go away just because of the one or the other biotic stress issue. And then at the end of the day, you end up just promoting 10% at each level of your promotion. So over the years, if you look at your 10 years data across your breeding pipeline, you will see that your selection at each and every stage is not more than 10 to 12%. It could be approximately, varies between 8 to 12% only. So that is a throughput bottleneck. Value, so ensures market leadership of your company or institute or organization, because you can deliver market leadership. If you have leaves looking bad, if there are leaf diseases on corn, farmer will be very far away, even if it is yielding. So that is a reality of life. Lowers production risk for the farmer. Faster and durable downability is one of the example you have seen very recently. So if you have biotic stress resilience, then it lowers the risk for farmer. Faster and durable improvements are possible. So these are the key diseases everybody knows, so I don't have to throw a lot of light. And these colored ones, dark colored ones, are the areas where corn is grown throughout the country. So you can look at very less area is I don't think anything is uncolored out of this graph. There are just few examples how this can be brought in. Very simple way could be you treat with physical mutagens, or you treat it with chemical mutagens. Nowadays anyway gene editing has come in, so you can create mutation through gene editing as well, and then you can just screen and take to M1, M2, M3 generations, and then you can do PCR screening, and then you can do gene tilling. So that's a very easy method to find out, not so easy as I am talking, but yeah, it's a comparatively better method for delivering the new alleles. Now, corn key diseases, published genes, QTLs and markers. Too much busy slide, but why I brought in only for one purpose. Those highlighted ones are only the examples where it has come to deployment. HT genes, and then Corteva has found those QTLs and implemented them. So those are the only examples. Probably in the hall you may be knowing more than me that there may be additional examples of the real-time implementation of these NBTs. But for me, this is what I could highlight when I tried to find out, like, what is the commercial implementation. So from this slide, I just want to show, or it is more like a thought-provoking kind of a question, that let us go ahead and see what additionally can be done and how much is the horizon available for improving the crop and really contributing to the Indian genetic gain. Now, that's the standard, like, I don't know why it is appearing like this on the screen, but can it appear as colored? Okay, no problem. Okay, not appearing. So anyway, I can tell you, CRISPR mostly it looks yellow, like, the genomic selection, mass and QTL. In the colored presentation, it all looks green because, most of scientists have implemented those technologies and they have come on the ground. Marker-assisted selection, it's an old thing, a lot of examples are there. Genomic selection has been implemented, and most of the places now people are trying for additional tools like, utilizing AI in that, utilizing additional new models like, random forest, and utilizing the covariates as other traits as covariates, like flowering time, like moisture. So those all things are being utilized as covariates. So additional things are happening, but that looks more of green. Promoter engineering, it has not even come out of concept. It is just inside the laboratory. R-gene parameting and single locus stacks. Somewhere it is yellow and somewhere it is pink only. So that is the status of these new NBTs application throughout the globe. And that I have compiled only for the corn crop, not for any other crop. So you can look at this is a prime crop, it is an industrial crop for the country, and that is the status of, like, NBT's utilization. Now, what could be the considerations and way forward? So one important thing that is of consideration is adding phenomics and process automation tools. So phenomics, what does it mean by? It is not just the drones, but anything. You can have robotics going across the ground. A robotic vehicle that goes across the ground uses a LiDAR camera and recognizes your bar tags and reads through the data. That could be one. Then another could be robotics utilized through, like, your high precision cameras utilized through your drone systems, which almost everybody knows, and then doing the, like, big data analysis through those images that are digitally captured. So, but yes, for really improving the genetic gain, I think this is one technology which our institutes should certainly deploy. What is the way forward for NBTs? Now, that's a very critical question. When you talk about decision-making consideration for the organizations, which includes universities also, not only the private sector. So gene editing system license, that, there is still some more clarity to be there. Cas9, that is the most popular system, but has lot of patents around it. Then Cas12, another system, then it has, that is the second popular choice. Now, newly evolving alternate system is TNP nuclease, TNPB. So that has got additional advantage because the protein size itself is very, very small and delivery methods will be easier. Then Open CRISPR is another newly patented platform that is almost open for everyone. So these could be, like, obtaining licenses or working with other institutions, that could be there. Then research service agreements can also be there. Now, if you look at why research service agreements, because, these technologies are changing day in and day out. Today, university deploys a particular type of, instrumentation and everything. Down the line, after 5 years, technology is going to change. So are we going to consider having our own genetic engineering labs everywhere, or, CRISPR labs everywhere in the universities, or we are going to have a center for excellence in just one place where, it is easier to replace the technology as soon as it changes? Then public-private partnership in gene editing projects is another possibility. So we can access the gene-edited products for commercialization through utilizing those, like, MOU framework. And then there could be co-development and various other partnership opportunities can also be there. Priorities for India, how they stand? Pan-genome variability, that is still a question for corn. We need to focus on that. Somebody has to focus on it, specifically for our corn. focus on biotic stress resilience, then focus on well-defined 3 to 5 gene targets per trait. So, like, rather than going random, we should, for every kind of trait that we want to do, we should have a focus on what we want to do exactly, and what are the gene targets there. Adopt germplasm independent technologies, now they are there. Protocols are there for direct transformation, integrations and partnerships. So, integration and partnership, yes, that is a national question, because mostly every institute has their own de novo, like, platforms doing it. We could have thought of a national platform where this can be done together. I think that is something that has to be brought to the leadership's attention. Probably they may, senior leaders are there, like our chairman, sir. Probably they can take it forward to the people who form the policies. Then field evaluations, how it could be done, and then enabling the adoption. So those are the questions for deployment of NBTs in the corn. That's it. Thank you.
Thank you, Dr. Satish. So, beginning with the statement that we need to touch something like, or increase it to 100 million tons in 2047, Dr. Satish has taken us through the status of the maize ecosystem with reference to the methodologies which can be used to enhance the various components of maize productivity, and with special emphasis on some of those tools to reduce the timing of development of technologies. Like, you need not use certain technologies if they are not recalcitrant to double applieds. Then you can go for the speed breeding facilities and so on and so forth. And then going through some of those latent technologies. I use the word latent technologies because many of them, they don't approach these technologies. Like, for example, the epigenetics. There's a lot to be done in that particular area. So a good summary of the new technologies that needs to be probably applied to take the country to next level in terms of increased productivity. Can I quickly have some questions for him? Yes, sir.
Yes, sir.
What is the status of corn oil? Because we see a lot of corn oil and many others. I have also been talking with CIMAT. They say they have excellent genotypes which can contribute. And as it is, we have a tremendous shortage of. Is there a segment which is trying to work on corn oil, or for India it is not a very profitable crop?
No, when we talk about corn oil, it comes in a kind of a ecosystem. As such alone, it is not being utilized. But industries which are working primarily on corn, when we talk about corn ethanol, then certainly all these components are thoroughly important for the industry. Because when they are taking out the ethanol, at that point of time, they take into consideration all these important aspects like corn oil, like protein in the DGS, the protein quality, and then even they go up to the analytics of protein digestibility as well. So that's an important thing.
It's an important thing according to you. I mean, that's one thing. Second one, can you little bit elaborate on maize lethal chlorosis virus and how this issue was addressed for Africa?
So what they have done is that for maize lethal necrosis virus, what has CIMIT has done basically, they have utilized they have gone through a project, and then through that they utilize the technology to confer the resistance for the gene. ICRISAT is also coming up, CG institutes have very coordinated these things. Now ICRISAT is also coming up with a platform where they are thinking about introducing global markers as well as doing the genomic selections effective in crops our Sri and millets also.
What is your opinion on soil health vis-a-vis maize?
So we have when we talk about soil health, yeah, that's a very pertinent question, because some of the thought process is that maize could be taking out a lot of resources from the soil. But then the thing is that we need to come forward with those systems, cropping systems, which can rejuvenate the soil health, as like, like in our farm also we have seen sorghum growing side by side, the till crop. So we need to come up with those crop rotations, or we need to come up with those recommendations which can actually make it possible. But utilizing the crop industrially, that too for the purpose of our exchequer, that is the reality of today. If we have to become nationally, like, independent, and we have to have a better exchange ratio in the country. So for that process, it will be important. But now the onus again back goes to the scientists only. Like, once upon a time when scientists have solved the question of wheat, lower productivity, bringing it to higher productivity. Same way today there may be a question that India is transforming into a maize crop as a commercial crop for us. Then these are the questions which probably we need to resolve.
I could add a point or two there. When you talked about the new technologies, they have used the CRISPR-Cas method to actually tailor the plant so that it could select the kind of microbiome that it needs in the soil. And that particularly enhances the entire population. So here is a place where you can actually make the plant in order to see that it selectively recruits the kind of microbiome that enhances the soil health and so on and so forth. Probably that could be an answer to his question.
Phosphorus uptake, nitrogen uptake, those are all the genes. They are naturally also available, sir. And they can be further edited. Thank you, sir.
Thank you, Dr. Sunil.
Thank you, sir. As Dr. Parikh is leaving, so we take this opportunity to thank him, and I request our chair to hand over the token of love and affection from University of Agriculture Sciences, Dharwad, to Dr. Parikh, sir. Sir, please. Sir. Thank you, sir. Now we'll have an online presentation from Dr. B.M. Prasanna, sir, Managing Director, BISA, New Delhi. Sir, can you please share your slides, sir?
Yeah, can you hear me? Can you hear me?
Yes, Dr. Prasanna, this is Krishna Raj from Dharwad. Hello, how are you?
Hi, Krishna, how are you?
Yeah, I'm doing fine.
Okay, let me project my presentation. Okay. Okay, I hope you can now see.
Yeah.
Yeah?
Yes, perfect.
Can you see the presentation?
Yes, it's perfect. Thank you.
Okay, should I start my presentation, Krishraj?
Yeah, please go ahead, sir.
Okay, thank you very much once again to Dr. Tikku, Dr. Krishna Kumar, and organizers of this meeting to allow me to talk on a topic that is close to my heart, that is how to strengthen the maize breeding and seed systems in the global south, based on my experience in sub-Saharan Africa, Asia, and Latin America. Okay, as the previous speaker has pointed out, there has been a rapidly growing demand for maize in Asia on diverse fronts, not only with regard to poultry feed or fodder or cattle feed, but also in terms of specialty maize and more recently utilization as biofuel. All this India needs to ramp up the not only production, but also productivity of maize in the country. In 2023, the global maize production was estimated at almost 1.16 billion metric tons across as many as 194 million hectares. And the global average productivity is 5.75 tons per hectare. This is significantly impacting maize utilization not only in the US Corn Belt but also across Africa as well as in America. But what is important is the tropical maize environments, especially in the global south, are inherently stress prone. If you can see the drought impacts in Africa from 1950 to 2021, all those red marked countries were severely impacted by drought stress. And this includes not only a total population that was affected, but also millions of or billions of dollars of crop loss that happened over the years due to abiotic stress. If you come to the South and Southeast Asia, what we are experiencing typically during the Kharif season is increasing temperature, not only daytime temperature, but also nighttime temperature. This was a picture taken between April to May 2024, where you can see several countries in South and Southeast Asia were severely impacted by the heat wave. Not only that, do the abiotic stresses are becoming more prevalent, but increasing incidence of transboundary pests and diseases can be seen in the tropical environments, whether it is the fall armyworm in Africa and Asia since 2016 in Africa, since 2018 in case of Asia, or the maize lethal necrosis in case of Eastern Africa, which happened in 2011 and still persists in Eastern Africa, although we could, through very concerted measures, stop the flow of this devastating disease into Southern Africa and West Africa. Tar spot complex, on the other hand, was earlier confined only to the Central America, but now we can see tar spot complex happening also in the US Corn Belt. Two particular diseases that are becoming increasing concern are the post-flowering stalk rots and the ear rots in case of maize in South and Southeast Asia. So maize-based agri-food systems, whether in Africa, Asia, and Latin America, need to be continuously protected from these devastating transboundary diseases and insect pests. The science behind maize breeding or crop breeding in general has changed significantly over the last 2 decades. Ever since the onset of molecular markers, there are now rapid developments with regard to high-density genotyping platforms and also sparking not only marker-assisted selection, but more recently genomic selection or genomic prediction. And thanks to the capacity to identify and clone genes, or even go deeper into the genome to identify causal variants, gene editing is now possible. Statistical designs and software is a less recognized, but a major advance that has happened in breeding. If you are a modern day breeder, you need to be thoroughly familiar with various statistical designs and software to analyze the data. Breeding data management and breeding analytics have become much more powerful than 15, 20 years back. Similarly, phenotyping advances have happened both on station and on farm, and coupled with rapid generation advancement through double haploidy in case of maize or speed breeding in case of crops other than maize. So all these are game changers in terms of modern day crop breeding. And that's why Mark Twain's quote on continuous improvement is better than delayed perfection really is relevant today because you cannot wait till all these platforms become much more powerful than they are. You need to continuously adapt to the changes that have been happening on multiple fronts that impact the efficiency and the success of a breeding program. CIMMYT's breeding for climate resilient maize revolves around well-established breeding schematics. not only in terms of population improvement, but also line derivation, hybrid formation, evaluation through various stages, and finally licensing. Coupled with all this are, I would consider, 5 major factors that are really important if we have to make an impactful breeding program. One, strong germplasm base is extremely important. Second most important aspect is what is your population improvement strategy and what kinds of primary and secondary traits are you selecting for in an efficient manner. The third one is what kind of germplasm testing network an organization has, both on station and on farm in the TPEs. TPE means target population of environments. The fourth important aspect is very well defined breeding schemes with integration of double haploidy, marker assisted selection, genomic selection or prediction, or rapid cycle genomic selection as we call it at CIMMYT. And the final most important thing is strong public private partnerships for product, not only for product development, but also for product delivery or scaling. So the advances that we use, phenotyping is fundamental no matter what new technologies in genomics have come about. But your capacity to unravel the differences in the phenotypes of the germplasm that you are testing, be it for drought stress or heat stress or waterlogging stress or disease resistance or insect resistance, is absolutely fundamental. So you need to have excellent phenotyping specialists together with people who can contribute both on the field-based as well as molecular breeding fronts. Thanks to these advances, even if you look at the CIMMYT's germplasm collection, we have around 25,000 landrace accessions in our germplasm bank at Mexico, of which around 15,384 maize land races have been genotyped completely. And this genotyping enabled us to understand the genetic similarities or dissimilarities amongst the land races that came from multiple countries across the global south, majority of them coming, of course, from Mexico. You can see here, these are all Mexican land races. And these Mexican land races are very different in their composition compared to many other countries across Americas or Asia. But it doesn't mean that not all these land races could be utilizable in breeding strategy. You need to understand what is the functional genetic diversity for a set of characters that you are mainly interested in. That's where we went for land races that came from drought-prone environments of many of these regions, analyzed them intensively, both for their molecular diversity as well as environmental diversity, and shifted this core germplasm panel concept into breeder panels that could be utilized in breeding strategies to diversify the genetic base in our breeding materials, especially for core traits such as drought tolerance or heat tolerance. So fundamental, therefore, in our strategy to utilize plant genetic resources in breeding programs is this capacity to understand or unravel the functional genetic diversity in your germplasm banks. And that's how CIMMYT contributed to the creation of what we call molecular atlases for maize as well as for wheat. And these molecular atlas in these two crops provides data, tools, and resources to allow the germplasm bank users, be it breeders or other researchers or extension agents, to identify the diversity of likely value for specific needs of breeding programs from the tens of thousands of germplasm accessions available, be it land races in case of maize or land races and wild relatives in case of wheat. So this is absolutely important. The plant genetic resource management has to change with the availability of powerful molecular tools and technologies that enable us to identify functional and relevant haplotypes for the diversity of traits that we use in our breeding strategies. The second most important thing is technologies to accelerate breeding cycles need to be implemented systematically. That's where the program that I led for almost 15 years at CIMMYT came up with the tropicalized maize haploid inducers. Initially, the first generation haploid inducers were brought out in 2012, and the second generation haploid inducers in 2017. And these haploid inducers, they are quite unique with almost 10 to 13% haploid induction rate. For example, our second generation tropical haploid inducers have been disseminated to almost 50 different research organizations, both public and private, across 18 countries in the global south. And not only we developed and utilized these tropicalized inducers, but we established maize double haploid development service to the national partners and small and medium enterprise seed companies by establishing 3 different research platforms, DH platforms. One at Kiboko in Kenya, the second one is Kunigal near Bangalore, and the third is Agua Fria in Mexico. And these DH platforms offer DH development service to national partners as well as SME seed companies. DH can become even more impactful if you combine this with molecular markers. So that's why any mature research organization, be it in maize, wheat, or any other crop, needs to have a well-established molecular genetics team. And this team needs to systematically progress from discovery to validation in independent populations, to validation in breeding populations, development of genotyping assays, and finally deployment of those breeder-ready markers for specific traits. And that's what we do. At each of these stages, we have a stage gate system where the researchers thoroughly thrash out what data is available, and is this data giving us confidence to move from discovery to validation to deployment stage. So this is a robust molecular marker pipeline for prioritized traits. And then once you come to breeder-ready markers, those validated molecular markers can be utilized routinely in forward breeding, marker-assisted forward breeding for allelic enrichment, rather than simply transferring the trait into 10-year-old, 15-year-old varieties. That marker-assisted backcrossing is not as powerful, in my view, compared to marker-assisted forward breeding, where you implement or utilize these markers routinely in your breeding strategies or in your breeding schematic. For those traits which are not amenable, which are not oligogenic, or 1 or 2 major genes or markers linked to them can cause significant phenotypic variance, you have to go through genomic selection or prediction for improvement of such complex traits. This is just a schematic to show how in CIMMYT global maize breeding program, we could save almost 30 to 40% time as well as cost of the breeding pipeline, while increasing the genetic gain almost by double. And this is, for example, Eastern Africa product profile 1, Eastern Africa product profile 2. This is what we call intermediate maturity. This is late maturity. This is highland maize breeding program. This is intermediate to late maturity in Southern Africa. And this is early and extra early maturity in Southern Africa. You can see a combination of traits being utilized for genomic prediction here, right from grain yield, anthesis date, plant height, ear height, striga tolerance, fall armyworm tolerance, GLS resistance, Starsicum leaf blight resistance. You can see a range: grain yield under low nitrogen, grain yield under drought tolerance, grain yield under optimum. So genomic selection or prediction is a powerful tool to utilize a smaller set of markers that cover the genome. Maybe not more than 3,000 to 5,000 markers can be utilized routinely once we have well-established training sets and the data, the breeding values of tester set can be then determined. So genomic selection or prediction can be used for multiple applications, for selecting high-value parents for your next cycle based upon genomic estimated breeding values, to reduce the breeding cycle time significantly, to undertake sparse phenotyping based on genotype relationship matrix, or to predict the crossing process for longer term genetic gain. All these things are no longer theory, they are actually done in some of our breeding programs, especially maize, for instance, in the global maize breeding program of CIMIT. A series of publications we brought out, right from how to utilize rapid cycling genomic selection in a multi-parent tropical maize population, to combined drought and waterlogging tolerance in tropical maize, or genomic prediction across years in a maize double haploid breeding program to accelerate early stage test cross testing, or maximizing the efficiency of genomic selection in a tropical breeding program. Plenty of publications, but I'm just showing a few of them to show that this has moved much beyond pilot or proof of concept stage to actual mainstreaming in breeding programs. So GRM based prediction, for example, this is how we moved from a test half, predict half strategy to utilization of historical data and training sets to now test a few and predict a lot. That means once your genomic relationship matrix are well established, you need not have to phenotype every test cross. But while you genotype every founder line, every line that has gone into formulating those crosses. So genotyping all, but phenotyping a few, and genomic estimated breeding values based upon well-defined genomic relationship matrices. The second most important thing I want to touch base here is about genetic gain analysis. Genetic gain analysis must become an intrinsic part of our breeding strategy. Annual assessment of genetic gains is a must in maize breeding program, for instance. Besides analyzing historical trends or genetic trends across, this is a classic paper that we published in 2022, where data from almost 4,150 advanced breeding trials conducted at 1,331 locations across 28 countries were analyzed over a period of 11 years, 2010 to 2020 data. This is all on-station data. And this on-station data showed that genetic trends for grain yield have reached up to 138 kgs per hectare per year in USA, 118 in case of South Asia, and 143 in case of Latin America. This is, remember, considering all the complex traits that we were talking about, like drought tolerance, heat tolerance, and disease resistance coupled with optimum grain yield. Not only on-station analysis, but we also analyzed more recently on-farm data. So you can compare then on-farm how much yield gain that you are getting compared to what is the yield gains that you are realizing on-station. So over a period of 2011 to 2023, the on-farm genetic gains were 76, 50, and 34 kgs per hectare per year in some of these breeding pipelines, for example, what I mentioned here, which is not bad at all. If you are getting such 2.5%, 1.6%, 1.1% compared to the base yield or average yield in 2011, that means significant progress has been made. It's more easy to get on-station genetic gains compared to even on-farm genetic gains where farmers utilize diverse management practices or diverse inputs. Even then, our gains were quite significant. So this is an absolute must in modern crop breeding programs. You need to put a strategy in place for on-station and on-farm genetic gain analysis. Someone was asking a question about MLN resistance. Breeding for MLN resistance, we made tremendous progress over the last few years. For example, when the disease first broke, almost 95% of the materials, advanced breeding materials in cement pipeline were highly vulnerable. You can see the mean was almost like in 2012, it's around 8. Come 2016, we have shifted this population mean in terms of resistance to almost 5, to 4, to almost 3.5. Now it's almost 3. So that shows, you can see a highly MLN resistant genotype compared to a susceptible line. So this facility that was established at Naivasha enabled us to systematically screen germplasm, identify resistant sources, analyze the molecular basis for resistance, and introgress molecular markers to transfer resistance from different genetic backgrounds into our breeding materials. So if you look at the new MLN resistant lines, which are CIMIT Kenya double haploid lines, you can see all these with around, on a 1 to 9 scale, they are all 2, compared to the susceptible checks, which are go all the way up to 8 or 7 or 8 or 9 even. So this shows the kind of progress that you can make even for a complex viral threat like MLN using breeding if you have a powerful genetic base and a multidisciplinary way of approaching a problem through dedicated facilities and dedicated strategy. The same way, in case of fall armyworm, when it broke in Africa in 2016, I could establish almost 16 screen houses at Kibako Farm, each of it around 1/3 of the size of an acre. And these greenhouses enabled us to screen thousands of germplasm accessions at our Kibako farm over the period 2000. For example, you can look at 2018, 19, 20, 21, 22, 23, 24, over 17,800 lines and over 2,000 advanced hybrids. Overall, about 20,000 germplasm entries have been screened from CIMIT against fall armyworm under artificial infestation in these greenhouses. This is a massive work. No public or private sector institution has undertaken such a massive work on insect pest resistance in maize through dedicated screening facilities. And the result of this, today we have released not only lines that have gone to over 90 institutions globally, but hybrids have been, fall armyworm tolerant hybrids have been released in Kenya, South Sudan, Zambia, Malawi, Ghana, and Zimbabwe. And they are already commercializing these CIMIT-derived fall armyworm tolerant white maize hybrids. Look at under no choice trials in the screen houses. That means entire chamber, almost 40 rows of maize of a single genotype or a single hybrid, infested twice at least artificially, one at the vegetative stage, another at the reproductive stage, and then analyzing both the foliar score as well as the ear scores after harvest. You can see a susceptible commercial check with not only very high foliar damage, but also ears that are damaged compared to a fall armyworm tolerant hybrid from CIMIT with much better harvest, much cleaner harvest, and much better foliar response. And that is the critical thing in the fall armyworm, breeding for fall armyworm resistance. Not just choice trials, but also no choice trials to validate the responses of those hybrids. And similar approach we have undertaken in Asia. Now we have fall armyworm tolerant yellow or orange maize hybrids coming from the CIMIT pipeline, which we are testing right now in several countries across South and Southeast Asia, including India, Lavopedia, Myanmar, Timor-Leste, Nepal, and Bhutan. And the process also has been initiated recently with the Philippines. Again, you can see a significant difference between a tolerant yellow or orange hybrid versus a susceptible hybrid. Gene editing is another powerful tool in the maize geneticist armory right now. This is the gene editing work we undertook in partnership with Corteva. You can see the resistant check, the susceptible check almost finished. This is a score of 9 on a 1 to 9 scale. The gene edited version of a susceptible line, this is the null. That means it has no editing done in that particular line, so highly susceptible compared to editing done. And you can see the drastic difference in the phenotype. So we have two approaches. One, editing a eukaryotic translation initiation factors, which have conferred resistance. The second approach is editing a peptidase gene on chromosome 6. Both these have yielded significantly positive results. The second paper is right now under review. In case of maize, not only a trait like MLN resistance, but you can also do gene editing for multiple traits. The genes underlying these traits like tassel branch number, tassel branch angle, kernel row number, ear prolificacy, leaf angle, or tillering habit, a number of traits have been already, the genes underlying them have been cloned and characterized, and the causal polymorphisms explored, and gene editing possibilities are increasingly now becoming available. China is clearly leading on that front. We need to now jointly evolve viable paths for commercialization of already existing genome-edited crops, besides overcoming IP and commercial bottlenecks to do gene editing on an array of other crops, including maize. Irrespective of the route we take, whether it is field-based breeding or genomics-assisted breeding, extensive on-farm trials are as important as on-station testing. In case of CIMMYT maize program, we conduct on-farm trials in Eastern and Southern Africa on over 2,000 sites in total. 2,000 sites. This is not a small number. In the last 3 years itself, the data has been collected from over 5,000 on-farm sites. What we then further did is to create a farm typology concept, not treating all the smallholder farmers as uniform and homogeneous, but to categorize them on the basis of household characteristics, their maize production characteristics, their input usage, etc., etc. So gaining a much greater understanding of product performance versus trait or product preferences vis-a-vis the farmer's typologies, and factoring this information into stage gate advancement of our hybrids. This is stage 5. The extensive regional on-farm trials is stage 5. Up till stage 4, it is on-station testing. So a selected set of hybrids then go into on-farm testing, and then we consider both on-station and on-farm data to identify well-suited hybrids for release under different target product profiles. All this means that the capacity of institutions to dynamically process large data sets, be it phenotypic, genotypic, pedigree data, environmental data, farmers management data, all these are extremely important. That capacity to process data and to take selection decisions. And that's where the human capacity becomes limited. You do need to utilize machine learning or deep learning models and embed them into your genomic assisted breeding strategy, and provide even more powerful predictive algorithms to analyze your data by combining this multi-layered data. This is what we wrote through in an article in 2024 on how to utilize artificial intelligence in plant breeding, especially taking the efforts that we are doing at CIMMYT together with partners. Similarly, we came up with another paper in 2022 on how smart breeding can be driven by big data, artificial intelligence, and integrated genomic environmic prediction. Ultimately, what I strongly believe is the need to democratize predictive breeding. predictive breeding is at present confined to a few advanced institutions, whether it is in CGIR or in some universities in the global north. But many institutions in the global south have very limited capacity to utilize predictive breeding due to various factors. Not only because of lack of well-defined breeding schemes, but the genotyping, even simple routine genotyping is people are not able to establish painless protocols. Education about when and how to apply genomic prediction, lack of computational expertise, logistical challenges related to genotyping analysis and making decisions within a short time frame required for breeding. So how do we bridge this gap? And how do we make even this guy become as powerful as this guy in terms of predictive breeding? That's the challenge for the years to come. For this, fundamental is to establish institutional data management framework. Breeding data at the present is confined to individuals' laptops or many a times in hard written field books and papers, and they all disappear once the person retires. This is not how breeding should be managed, or breeding data needs to be managed. If data-driven decision making has to happen, you need to have end-to-end software system that can connect haplotypes, markers, ancestors, germplasm, samples, seed packages, plots, trials, sites, phenotypes, environments, and product profiles. This is like a galaxy. How you visualize the stars in a galaxy are connected. That's exactly what needs to happen. And that will enable us, together with powerful analytical platforms, automating the GEBVs, PEBVs, GCA, SCA estimates, rich visualization of data. And then breeders can select what line I should use as a founder parent for what specific trait, what kind of optimal cross combinations could be maintained. How do I use sparse phenotyping or sparse test crossing in order to reduce the cost of my breeding programs? These are fundamentally important in modern crop breeding strategies. Coming to the seed systems, it's not simply adequate to release thousands of crop varieties and almost 90% of them never see the light of the day. What is really important is to have much better data and insights even before you release varieties, improved quality assurance and quality control system once a variety is released and put in the market, better strategies for gender and social inclusion, targeted reach of those varieties, digitalization of our seed roadmaps, and creating seed villages, especially when opportunities for commercialization are limited in certain crops. This means we need to scale up the digital and genomic tools and technologies to transform business processes and operations and establish powerful public-private producer partnerships. And that's what we have done in case of maize program by creating innovative product licensing models in the first place. So just look at this data. Over the last few years, 263 partners, of which 209 are private sector, are holding licenses across the world for CIMMYT maize products. We have released 270 hybrids through this process, besides 11 OPVs only for targeted market segments. And the number of countries having licenses or institutions coming from those countries are almost 76. This is the largest geographic footprint of any CGIR breeding program across the world. And it is based upon geographical limited exclusive licensing models to public as well as private sector partners. The result of all this, when I joined CIMMYT in 2010, drought-tolerant maize occupied not more than 0.5 million hectares. Today, it occupies almost 8.5 million hectares in just 14 years, reaching 9.8 million households and benefiting 60 million people. certified seed production of our CIMMYT-related varieties. The yield benefit, which has been actually estimated by economists in different countries, ranges from 500 to 750 kgs per hectare for drought-tolerant maize adopters, providing 9 months of food at no additional cost to a family. The annual economic impact of CIMMYT-related improved maize germplasm in Eastern and Southern Africa alone is 1.3 billion US dollars. So that is a powerful impact assessment study. All this is possible because of dedicated seed system specialists, excellent public-private partnerships, innovative product licensing models, and targeted reach of drought-vulnerable populations across sub-Saharan Africa. Asia is still at its infancy with regard to deployment of climate-resilient maize hybrids. But what we have created in the last 10-15 years is a unique set of drought and drought plus heat tolerant maize hybrids and released across Sri Lanka, India, Bangladesh, Nepal, and Pakistan and Bhutan. So, and these hybrids are now being scaled up. For example, this is a project funded by Ministry of Agriculture and Farmers Welfare, where we have taken specific districts where the Kharif maize productivity is low, identified specific climate resilient maize hybrids from CIMMYT germplasm, and now in collaboration with state departments of agriculture, state agriculture universities, innovative maize farmers, farmers producer organizations, SME seed enterprises, deploying these climate resilient maize hybrids in those particular districts where clusters of districts in several states across India where the Kharif maize productivity is low. So friends, this is in brief what I would like to highlight in my presentation today, and would be happy to answer any questions. Thank you.
Thank you, Dr. Prasanna. That was a end-to-end story. A concentrated information based on breeding dynamics, which included genotyping, phenotyping, and then the sheer size of experiments which leads to the development of algorithms to sort out the issues with respect to the maize breeding. You've touched upon several aspects, and I'm sure that the audience here have been treated to a beautiful story on maize on their palate. Thank you, Dr. Prasanna. Also, it's wonderful for you to have summarized the great American humorist Mark Twain when he talks about small developments which are useful rather than trying to, be a whiz in that particular area. Thank you very much, Dr. Prasanna. Once again, it was wonderful hearing you. I'm sure that's the message that you should get and you will be getting from all across the audience here. Now I request the audience to have some questions, and I'm seeing the hands of Dr. Tiku.
Please put on the video. I cannot see the video. Colleagues, can you switch on the video if possible? Otherwise, I will hear.
As usual, excellent. I mean, no words can express enough what you have said. And I've been following your work for a long, long time. I have only a request. I don't have a question. Why can't we recreate that public-private partnership in the sense you have done in CIMMYT? We don't have. I'm telling you, I attended my first public-private partnership kind of dialogue when Dr. Chadda had it in Trichur in 1989. This is 2026. I don't see even one project that has reached real public delivery. We are not talking of, this is our hybrid, you license. That is not PPP. For me, PPPs are like you did in MLN. I've been also talking to Suresh very often. So can you help now that you are in Delhi? Thank you.
Absolutely important, sir. I think in crops like maize, where seed companies have to play a powerful role in technology delivery, it's absolute must that we need to have these strong partnerships. Without those partnerships, the impact and reach of our hybrids or our varieties will remain very, very limited. That's why it is not easy, even at CIMIT, to champion that innovative licensing models. One had to think through a lot. One had to take everybody into consonance, answer many questions raised by different donor agencies. But today, the story itself is so powerful and successful that they recognize that these models need to be replicated across different CGIAR centers themselves. So I was happy that I could do that, and I am a powerful advocate of public-private partnerships, especially not just in terms of technology scaling, but also in terms of technology development.
Yes.
We collaborate with so many institutions and make them true partners in executing our breeding funnel, breeding strategy itself. They don't have to come necessarily at the end. They can be systematically embedded in our strategy for product development itself. So there are lots of things that one can do. Yeah. Thank you.
Thank you.
Thank
sir.
you, Dr.
Thank you.
Prasanna. Now I have Dr. Krishna Kumar has a question for you.
To answer Dr. Tiku's question, and also, since you know, Dr. Prasanna approached ICR. I was at that time DDG, and though maize was not under me, the double haploid facility, I had to swim against the tide. And then today it is in Kunigal, a wonderful collaboration open up to anybody who wants to use the double haploid facility, and it is contributing a lot. I mean, just giving an example, just to say that, I think on the day
I
of the,
still remember that meeting when I came to your
Yeah.
office.
So-
And
so-
thank you so much for all your support.
Yeah, the 2-3 quick questions. First of all, compliments for such a mega scale evaluation of germplasm for the newly introduced
Yes.
borer, that, I mean, the pest that was there. But if the mechanism of resistance is antibiosis, how fit it is for human and animal consumption? That is my first question to you, because antibiosis by in itself, you can imagine that it may not be very desirable purely for a human or animal consumption, for which a significant proportion is being taken. My second question is with respect to maize lethal chlorosis. It is two viruses acting together, one transmitted by thrips and another transmitted by aphid, and together in also some beetles are attributed. In such a scenario, when normally we see that you develop resistance to the disease, the one which is suppressed begins to make an expression in many crops, as we have seen in papaya, as we have seen in okra and many others. The one which is weaker begins to assume a dominant position. I'm not sure how it is in case of maize lethal chlorosis. My small,
Thank you, sir.
my
So-
third, my only one small anecdote for the third point is, are we mixing up drought, moisture stress, and heat tolerance into one, whereas there are 2-3 independent events?
Okay, all three are very, very nice questions. The first one about the fall armyworm resistance, it is those compounds that we analyzed, even what makes certain inbred lines of maize fall armyworm tolerant naturally or native genetic resistance compared to the susceptible ones. This work was done in partnership with CIRAD France. And the compounds that are elicited are not ones which interfere with the ear taste or the kernel taste or kernel culinary properties. But these are the compounds that deter the insect, the larvae, from feeding on. They are like jasmonates, for example, or terpenoids, beta caryophyllin. These are secondary metabolites that are particularly expressed in response to the insect attack, and it is a polygenic resistance. Unlike BTKs, way that antibiosis is because of a very powerful but easily defeatable because it is single gene or oligogenic. That's why I would on any day prefer a falamivarm native genetic resistance compared to even BT. Or if you have to introduce BT, introduce it into a native genetic resistant background. Then you have a much better insect resistance management strategy compared to transferring the BT gene into any susceptible background. So firstly, it's polygenic. Secondly, there are multiple mechanisms associated with native genetic resistance to falamivarm, about which we are beginning to understand what are those metabolites. But these metabolites do not interfere with the taste or the yield or other important attributes of related to the kernels. The second one with regard to MLN viruses, you are right that this is a complex of two viruses, the maize chlorotic mottle virus and the sugarcane mosaic virus, or any of the member of the Potiviridae. But that's the reason why CIMMYT went for simultaneously targeting two specific genes. One is a peptidase gene on chromosome 6, and another is the eukaryotic translation initiation factors on chromosome 3. Instead of simply going for one particular resistance gene, we are targeting two different resistance mechanisms. One is the translation initiation, another is the peptidase mechanism. So these mechanisms do not necessarily suppress only one particular virus here, like MCMV. It has an obvious effect on both MCMV as well as SCMV. And therefore, it doesn't make one virus stronger than the other. It attacks both instead of going for only one. So, by the way, gene editing is only accelerating the process. We were able to even breed without gene editing multiple resistant lines, but it took us about 3 to 4, 5 years to get those resistant lines. But what we started with 1 or 2 now have become more than 60 to 70 resistant lines, MLN resistant lines. So it's again a powerful story of how this resistance could be accomplished through breeding. The third question is about, sir, sorry, I could not remember the third one, the third point.
Are we mixing up heat tolerance?
Oh, okay. That's a very good question. Drought tolerance and heat tolerance are not same. Physiologically, heat tolerance is not just a kind of a lack of water availability, but also a vapor pressure deficit. It's the temperature coupled with relative humidity. That's what creates the VPD. So CIMMYT has established a network of sites for phenotyping for heat stress tolerance. Typically, we do it by planting in February and harvesting during the spring season. And that creates a very strong daytime as well as nighttime temperature stress. So drought tolerance, on the other hand, is related but not similar. So we have drought tolerant lines that are highly susceptible to heat stress. We have heat stress lines which are partially drought tolerant, and we have lines which are tolerant to both drought and heat stress. So you can get all the three combinations from the CIMMYT germplasm because physiologically and genetically they are not completely linked. But you can still mobilize both the traits into a single line or a hybrid.
Yes, sir.
Dr. Prasanna ji.
Patil sir, namaskar.
Namaste, good afternoon. Thank you very much for your excellent talk. We expected you to be offline. So anyway, you have made it in spite of your busy schedule.